The last class, what we did, we actually revised what was done in the class before that. Okay, who has started the recording? Thank you from my behalf. But if you have started, then please don't stop after that. Okay, thank you. So in the last class, we studied two things. Number one, how do we define arbitrary product of sets? So how did we define Cartesian product of arbitrary sets? Okay, and after that, what we did you all forget? After that, we learned about axiom of choice. Okay.
Statement of axiom.
Yes,
Good
Miss
afternoon,
Teju.
ma'am.
Good afternoon, Shraddha. So, does anyone have any problem in understanding what the Cartesian product of arbitrary sets was? If you
No,
have any
ma'am, I
problem,
had
then
no
just
problem.
please. Okay, anyone else? Because it's a class of more than 60 students. Everyone understood very well what was the Cartesian product of arbitrary sets.
मैं ये बता दूं कि उसमें अल्फा बिलोंग्स टू आर था ना कार्टेशियन प्रोडक्ट में, वो उसकी जरूरत क्यों पड़ी जबकि सब काम तो नेचुरल नंबर पे हो रहा था?
Okay, Bilal. So Bilal is asking what was the need of Cartesian product of sets from R, right?
यस मैम.
Our example was that we had X alpha. We had the sets non-empty sets X alpha for each alpha belongs to R, right? That's what you are saying.
यस
Bilal,
मैम.
please unmute. Yeah. So इसकी जरूरत क्या पड़ी? What was the need? So that is the whole point. We had arbitrary, so uncountably many large number of sets, right? We wanted to define their Cartesian product. So it's just an example of an index set. R is an example of an index set.
मैम आपकी
Okay.
स्क्रीन प्रेजेंट नहीं हो रही है.
हो
नहीं
रही
हो
है.
रही है.
हो रही है, विजिबल है.
हो रही है. Harsha,
It's
please
visible.
refresh. Please refresh, Harsha. Okay, so I'll just repeat again. So what happened was we knew Cartesian product of x1 cross xn. That means we knew what was that. It was classically defined to be ordered tuple x1 x2 xn such that xi belongs to capital Xi for all I. Right? And from that we did an identification. Our aim was to get rid of the order. Because we wanted to get rid of the order, so we identified each such tuple as a function from 1 to n to union of xi such that, say if f was the function, so f of I should belongs to capital Xi. Then we identified x1 x2 dot 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 xn to be the range set of f. Okay, so for such a choice of, for f to be such a function with a restriction condition, we call that to be a choice function, right?
यस मैम.
यस मैम.
Yes, ma'am.
Okay, so from there we defined if we have a collection, of arbitrary sets xi, I belongs to I, okay, then we define the product of these xi's to be collection of all the choice functions. Okay, so we define product of xi I in I to be the collection of all choice functions, right? That means all the functions from I to union of xi I in I such that we have a restriction condition. That means fi should belongs to capital Xi for all I. Should I assume that everyone knows this now? So, yeah, anyone, someone unmuted. Is there any doubt? See,
No,
it's
ma'am,
not,
no problem.
it is actually not the thing like to get in the first time. So if you have any doubts, you can ask me again. So we then had the axiom of choice. It just says that this product is actually a non-empty set. Okay, whenever we have xi is to be non-empty for all I, then this product is non-empty. That means we have existence of at least one choice function. Okay, so we have an equivalent formulation of axiom of choice. That means which says that we have an existence of choice sets. Equivalent formulation, existence of choice sets. That means what? It's a function, then it's a set. So suppose we have an arbitrary collection of non-empty sets. Okay, if we have an arbitrary collection of non-empty sets such that they are pairwise disjoint, then we can say, I think I should write, yeah, if we have an arbitrary collection of non-empty pairwise disjoint sets, then okay, then there exists a set E subset of union of xi such that E intersection xi is a singleton for each I. Okay, do you understand?
मैम सिंगलटन ये क्या है इसमें
Singleton set?
नहीं मैम सिंगल सेट तो पता है इसमें मतलब ई इंटरसेक्शन ऐसा ही ये सिंगलटन कैसे हो
C intersection xi कैसे हुआ? यही हमारा चॉइस फंक्शन का इस टाइप का ही हम चूज करना चाहते हैं. That is why I am saying that this is a choice set. We have an existence of choice sets. Okay?
ओके
Okay.
Ma'am, please explain it once again.
Okay. So axiom of choice said that the product of arbitrary sets was non-empty. That means we have at least one choice function. So I am saying the equivalent formulation, like this can be stated as an equivalent result, which says we have existence of choice sets. Choice sets means suppose we have an arbitrary collection of non-empty pairwise disjoint sets. Okay, then we can always choose a set E union in subset of the union of all these xi's such that whenever we intersect E with any single one, then we will always get a singleton element. So you try to say, think it. Yeah. Suppose again suppose we had only a finite collection, say x1, x2, xn. Okay, they are pairwise disjoint. Okay, let me take an example. Suppose this is the interval, say 1 to 1.5. This is 2 to 2.5. This is n to n.5. They are pairwise disjoint, non-empty sets of R. Yes or no?
Yes, ma'am.
Yes,
Yes,
Exactly.
ma'am.
ma'am.
So they are pairwise disjoint, non-empty set. If I take E to be 1 to n, then this E is actually contained in union of xi's, right? And E
Yeah.
intersection xi is the singleton set. This case is actually equals to I. So now this was a particular example. Okay, we had finite number of sets. We know that if they are pairwise disjoint, I can just singly pick one element from each and then make such a choice. If I make such a choice that picking an element from each of these, then I can choose a subset of the union such that if I intersect with just one set, I'll get a singleton element. Okay,
Yes, ma'am. Got it.
Yes,
you
ma'am.
got it. So axiom of choice, just it is just an assertion that the same thing which you are doing in for a finite case, the same type of existence of choice set, I'll call this as a choice set. This E such that E is contained in union of xi with E intersection xi singleton, I'll call E to be a choice set. Okay, axiom of choice now says that we can always have a choice set no matter how many sets we have. Arbitrary collection of sets, right?
Yes,
It's
ma'am.
just a
Ma'am,
way. Yeah.
ma'am, is there any reason or query behind that we have at least one choice set, or it is just an observation we have seen through many of the questions?
Okay. So first of all, it is implication of axiom of choice, but it actually also implies the axiom of choice. So we say that it is an equivalent formulation. Okay. If two statement implies each other, then we say that they are equivalent. They are nothing but the same. Okay,
Okay,
so
ma'am.
if we
Okay,
assume
ma'am.
this, we can show this, and if we assume this, we can show this. So can you show it yourself? Can you at least try? Can someone at least try in showing this? Suppose this is 1 and this is 2. So now my claim is 1 implies 2. Can anyone try? At least try. At least, okay.
Yeah, ma'am, we can try.
Just so if you can try, then just like proceed with me. So what is first? Uh, what is 2? What do we want to prove?
We want to prove an set which is having elements from all the sets.
Yeah, very good. If we have a non-empty collection of pairwise disjoint sets, then we just want to say that there exists a choice set,
Yes.
right? We want to show
Yeah.
existence of choice set, but before proving, I want to make some assumption, right? So first of all,
Hello.
I will
Range of
assume,
any choice function.
please repeat, I didn't understood.
Take
Let
range of
X
any
be.
choice function.
Okay, so I'll just write, okay? So I have an assumption. So I assume let EI's, sorry, let XI, I in I be a collection of non-empty pairwise disjoint sets. Okay, so why I am writing this proof? It's a way to write any proof in mathematics. Okay, you must have learned this from your BSc, but I'm just trying to give you a flavor again. So if I want to show some statement in mathematics, okay, then how should I write? So it's a very important technique to write any proof. You can't just like say that it just follows. So if I am trying to show 1 implies 2, I am making one assumption. That means I have a non-empty collection of pairwise disjoint sets, right? So, and I want to prove something. What do I want to prove? I want to prove that there exists a choice set, right? Choice set means that is a choice set E. That means E is contained in union of Xi and E intersection Xi is singleton set, is a singleton set for each I, right? So now tell me, how
Yes.
should we proceed? Yes, Bilal, how should we proceed? Okay, so now you want
सर
to, yes, please. Okay,
इसमें तो इसमें सबसे पहले आर्बिट्री सेट लेंगे ना, और फिर उसके बाद
ओके, एक्साई जो कलेक्शन है हमारे पास आर्बिट्रेरी है, वो हमने ऑलरेडी ले लिया है।
मैम
हाँ, यस अभिषेक।
can we can we take a choice function and this answer to become E?
Shabash, very good Abhishek. So see, I wanted to prove something, but I should make use of the fact that I am given something. Okay, we are provided that one holds. That means if I, what was one? One says that if I had a non-empty collection, if I had a non-empty collection of functions, then there always exists a choice function. So by our assumption and that one holds true, since one holds true, this implies there exists a choice function, right? Choice function f, that means f from I to union of xi such that what?
F of I belongs to Xi.
Very good. F of I belongs to xi for all I, right? So you see, we want what? We want a subset of union of xi, right? We want a subset of union of xi. But if you try to see, the image of f is also a subset of union of xi. What I'm saying is, the image of f is a subset of union of xi, right? So my question is, does it satisfies our choice, our requirement?
Not now.
Not now. So I'll just show that it does satisfy our requirement. Okay, so I'll say that answer is yes. How? So first of all, for a choice, yes.
Ma'am, we can say that since fi map to fi image is xi,
Uh-huh.
and ma'am
Yeah. That's what I'm trying to say now. Okay, thank you, Rohit. So to be a choice set, I have two requirements, that it should be a subset of union of xi and E intersection xi should be singleton set. So the number one thing is true. So first of all, I'm claiming that, oh, sorry. I take E to be f of I such that I is in I. Now, E intersection xi is what?
Singleton.
Singleton fi.
Singleton FI.
Yeah, but what? But we have a problem. What is the problem? That means I can have fi equals to fj for some I not equals to j, or problems. So I'm just saying I have problems. That means either I can have two elements same, right? I can have fi to be equals to fj, or I can have fi not equals to fj, but fi and fj both belongs to sorry, xi intersection xj for some I not equals to j. These are the problem. Now this happens if this happens, then E
But these
intersection
were
xi
pairwise disjoint.
will not
Yes,
be. Yeah, that's what I'm saying. But if this happens, then E intersection xi will not be singleton. But because if I take E intersection xi intersection with E intersection xj now, it is nothing but E intersection xi intersection xj, which is E intersection the empty set, which is empty. Therefore, this is correct. So it's just an observation. Got it?
मैम
Yes, ma'am.
Yes.
मैम सेकंड प्रॉब्लम सेकंड समझ नहीं
हाँ।
आया.
प्रॉब्लम सेकंड में मैं इतना कह रही हूँ कि हो सकता है कि FIs का कलेक्शन है E. E is the collection of FIs. So any element of E is the form of FI, FJ, FK, FL, whatever. Right? So I am
Yes.
saying it might happen that we have 2 points, FI and FJ, both in XI intersection XJ. That means these are 2 points which are in XI and XJ as well. So this will make that E intersection XI contains both Fi and Fj. So it will not be a singleton then. So all of this trouble will be solved if I just show that if I take E intersection Xi with any E intersection Xj for I not equals to j, then it is empty. Therefore, this is a singleton set. Okay?
Okay, ma'am.
Okay. So one part of the proof is done. That means we had shown that 1 implies 2. Now we'll show that my claim is 2 implies 1. Okay. So again, now I have to make some assumption, right? I want to prove something. Now I want to prove one. One was what? One says that if I have a collection of non-empty sets, then the product is non-empty, right? So I have to make some assumptions. My assumption are what? I have just let xi be an arbitrary family of non-empty sets, right? So I want to show what? I want to prove now. I want to prove what? I want to prove that there exists at least one choice function. So if I want to show existence of one choice function, so I should know what is a choice function. A choice function is nothing but a function from I to union of xi such that f at I is in capital Xi for all I. This is what I want to say. But now see, we have a problem. In this part, we have made an assumption that right? What, Abhishek?
मैम assumptions के अंदर अपने को E को डिफाइन करना पड़ेगा ना. E is our assumption.
No.
Because
E is not our assumption. What I'm trying to say is that how to write a proof. I am saying that I want to show that the statement 1 is correct. I want to show that this statement is correct. Okay?
Yeah.
To show that this statement is correct, I need to assume some basic things that we have a collection of non-empty sets. So that is what I'm trying to write as an assumption, and that is what I'm trying to write as a to-prove statement. Okay, so as an assumption, I am saying that we have an arbitrary collection of non-empty sets. And as a to-prove statement, I am trying to say that there exists at least one choice function. That means f from I to union xi such that fi is in capital Xi for all I. Okay.
Ma'am, but statement
Ma'am?
2 have a if E set.
Exactly.
So what
The
about
मतलब
that?
मैम प्रूफ करने में हम वो ई का यूज करेंगे.
प्रूफ करने में हमें ई का यूज करना है.
हाँ.
क्योंकि हमें formulation 2 क्या कहता है? Formulation 2 says that we have a choice set E. So how do we make a choice set? But before that, see that in 2 we require non-empty pairwise disjoint sets. We don't have pairwise disjoint sets now. We do not have pairwise disjoint set. We just have non-empty sets.
Yeah, ma'am.
So there is a problem. We cannot just apply to. In order to apply to, I'll just make a trick. That means I am not just I'm not considering family xi now. I will consider the family. I'll define yi to be tuples xi with I. That means xi I such that xi is in capital Xi. Okay. Now you see that yi are the collection yi is a non-empty collection of pairwise disjoint sets. Do you agree?
Yes, ma'am.
Okay. So you all agree that we know that xi's were not disjoint sorry, pairwise disjoint. They were indeed non-empty. So if I take this form of tuples, then yi is non-empty. Also, it is pairwise disjoint. Because you know, if I take any other j, then the second coordinate will never be the same. So it is by sure non-empty collection of pairwise disjoint sets. So now if I have a non-empty collection of pairwise disjoint sets, since 2 holds true.
Ma'am?
Yes.
Ma'am, why yi is the collection of ordered pair, no, ma'am?
It's sort of yes.
Yes, ma'am. If it is not ordered pair, then ma'am thing will be not valid. What you saying that?
Yeah. That's what I'm saying. It's yes, ordered pair, but I had to make this ordered pair because I wanted a pairwise disjoint family.
Okay, ma'am. Thank you, ma'am.
To apply to, I need pairwise disjoint families. So now if I have a non-empty collection of pairwise disjoint sets, I can apply to now. So since 2 holds true, there exists a choice set. There exists a choice set. What was a choice set? That means E contained in union of yi and E intersection yi is a singleton set for all I. Okay. So now E intersection yi is a singleton set. So I can say that E intersection yi is some xi with I. Right. So what we want?
Ma'am.
We want a function from I to union of xi. What do I have? I have I and xi, a singleton set, which is contained in union of say yi. That means what? That means suppose I try to define a function now from I to union of xi. by this I is mapped to this particular xi. Then this is a well-defined function. How it is a well-defined function? How is it a well-defined function?
When I
Because
equals
is
to say
corresponding
when
I,
xi equals
there
to
exists an exercise
Very good.
in
It is
X.
well-defined. It is well-defined. F is well-defined because E intersection yi is a singleton set. So, therefore, I cannot map any I cannot be mapped to two different elements. That's what we want for a function to be well defined. Nah? We cannot map one point to too many functions, too many points. So,
Yes, ma'am.
1 1. Is there any problem? We proved this two part also. I know it's a bit to take. Okay. It takes a little bit time to digest these proofs, but if you learn these ones, then it will be very beneficial to you. Okay, so if you have any part in this proof, then just inform me, please. I assume that you all
Ma'am,
understood. Yes, yes,
ma'am,
Rohit.
ma'am, there was doubt from this part also, but previous class also. Ma'am,
Okay.
it was question is that, ma'am, as fi
Okay.
is mapping to xi,
Uh-huh.
then how it is
Fi,
going map?
see, Fi is not, F is mapping from I to union of Xi with Fi
Yes, ma'am.
in Xi.
Okay,
So what
ma'am.
is the problem here?
Ma'am,
I didn't understand, sorry.
yes, ma'am. I wanted to ask that if I can choose any element of xi or it is any particular element of xi. Suppose that, ma'am, in this case, when we are making the same, when we are taking the when we have formed the sort set yi,
Uh-huh.
at that time, ma'am, we have means for that we have chosen any xi belongs to any element of any element from xi, and with respect to that we have mapped xi comma I.
Okay.
Hello.
Yes,
Yes,
Rohit.
ma'am. Yes, ma'am. In that case, ma'am, when we are looking for the choice function, at that moment, ma'am, we can choose any element from xi set.
Okay, see, what you are trying to say is fair enough. You are trying to say that we can choose any element xi. But the whole
Yes, ma'am.
point is this. A choice set, for a choice set, we just have one particular point from each xi, no matter what the point is. But now, the exam of choice just say that there exists at least one choice function. So I am just choosing a choice set. Okay, so I'll just highlight this a. So a choice set means I am going to one particular fixed choice set. This xi can
Okay.
be any of the I, but now I have fixed this one. This is one choice. Okay, this is
Yes,
a
ma'am. Thank you.
fixed choice.
Okay, ma'am.
Okay,
Yes,
fair
ma'am. Thank you,
enough.
ma'am.
Anything else? So now we proved exam of choice has two equivalent formulations. That means we have exam of choice in two equivalent formulation. That means existence of choice functions and existence of choice sets. Okay, so now here I want to point out something, that by the same method as above, we can show that if xi is any non-empty collection of sets, any collection of non-empty sets, then whether now we have no condition on disjointness. Okay, if we have just any collection of non-empty set, then we can again choose a choice set. Again have a choice set. How? In the same way. Okay, so it can be proved by any of these 2 points. Okay, so I will just say one simple one, that if I take any choice function, okay, choice function is there by the exam of choice, that f with the choice function, then I can choose E to be Fi's again. Then now this E intersection Xi may not be singleton. Why? As suppose we had earlier 2 conditions, problem 1 and problem 2. If I just copy these 2 statements, if I'm just copying these statements, let's see that in both of these cases, E intersection Xi is not just equal to singleton Fi. Please just try to see that. Okay. So now I want to again repeat something. I have already told you before that exam of choice is actually equivalent to Zorn's lemma. Okay, there are many other equivalent formulation of axiom of choice as well. Okay, so actually in particular these proofs are not easy. So therefore I'm just time and again stating these facts. The proofs are not easy, but these the above one, that means, but where happened? Yeah, but its proof, these 2 equivalent formulation, it was quite possible. So therefore I used this one. Okay, but some proofs are not easy, but it is important to know the fact that both of them are equivalent. Okay, so now as an application of exam of choice, uh, application of exam of choice, I'll state a result that every infinite set contains a countable set. You remember what a countable set was?
Yeah, ma'am.
Yes.
Yes, ma'am.
Yes, ma'am.
Bijection
Very
with
good.
natural number.
Very good. Bijection with natural numbers. So every infinite set contains a countable set. Now I will try to give you a proof which is already there in the book. Okay, proof in the book Prentice and Perkins. Yes.
Ma'am, when you talk about arbitrary means you have assumed that it is infinite or uncountable.
Okay, arbitrary means it can be finite, infinite, countably infinite, uncountable infinite, anything. Arbitrary means anything. Okay.
Okay, ma'am.
So I'll first of all, you see this statement. Okay, every infinite set contains a countable set. Okay, so I'll now tell you the proof which is there in the book Prentice and Birkinshaw. So it says that suppose X is a infinite set. X is an infinite set. If X is an infinite set, that it directly means that X is non-empty, right? This implies X is non-empty.
Yeah.
So we choose a point, say A1 in X. I can choose any point A1 in X. Right. So now if I take X minus singleton A, X minus singleton A. See, since X was infinite, then
This is also non-empty.
X minus A1 is also an infinite set.
Yes, ma'am.
Right. X minus A1 is also infinite, because if it is not infinite, then it means that X is equals to, if not, this means that X minus A1 is actually equals to some finite set. This will implies that X is equals to A1 union a finite set, which is again a finite set. Right. So this is not like this. We should know that X minus A1 is also infinite. If X minus A1 is also infinite, that means in particular this is non-empty. Right. So this means that X minus A1 is non-empty. So I can choose A2 in X minus A1. Right. So I have 2 points, 2 different points A1 and A2 from X itself. Right. So I'm saying that A1 and A2 are distinct points from X. So what I'm trying to say is, in a similar fashion, I can choose. Okay, I am saying that in a similar way, I can choose an in X minus A1 up to an minus 1, and all these points are distinct. So therefore, if I just take, say, E to be A1, A2, that means all such points AIs, then E is a subset of X definitely, and E is countable. Okay.
Yes, ma'am.
So do you,
Yes, ma'am.
so now what is the problem with this thing? I'm saying that it has a problem. It has a problem. That means the problem is, in a similar way we can choose this. It was true, but what? Sorry. But what happened? Okay. But this is an infinite process. What I was trying to say in the last class, that this is an infinite process. I have to like keep on picking points arbitrary many times. Okay. This is an
Yes,
infinite
ma'am.
process. I want to like finish it in a finite time, so that I can say, yeah, this is particularly a set which is countable and a subset of X. So axiom of choice, in this particular case, axiom of choice just helps us, but it's not just directly this formulation of axiom of choice. Okay, these two formulation does not help here. The formulation which helps here is the dependent axiom of choice. Okay, just Google it. I will not like say further tell you what is the dependent axiom of choice or anything, but I am saying that the problem with this proof was that it was an infinite process which was not happening to finish in like a finite time. So therefore the proof is not a correct one, not completely correct. It is like, I can argue it is correct in some way. It will be correct if I add 2-3 lines here, but it has some problems. Okay, so we can use dependent axiom of choice. So why I am saying dependent axiom of choice, you see that if I take the point an, so choosing an is dependent on the previous points, a1 up to an minus 1. Okay?
Yes, ma'am.
Okay. So dependent exam of choice is the version. So we will not like prove this thing here. This obviously this will not be asked in your exam, this proof. Okay. But if you are interested, you can just Google it. Okay. And it's actually in one book. I guess it was in the book. Oh, yeah. It was in the book Naive Set Theory by P.R. Helmholtz. P.R. Helmholtz. P.R. Helmholtz was actually a very great teacher. So if you want to see, you can just Google it. So now after this we have I have a warning notation. I'll just move on to now. You see that in some way when we are actually dealing with countability and uncountability, the exam of choice was there to save us, right? So I'll now just state some theorems regarding regarding countability and uncountability. Okay, but first of all, I have a word notation warning. So terminology warning. Okay, so in some books, actually what happens is they use countable to say that it is either finite or countably infinite. Okay, in some books it says this thing, but for us countable means countably infinite. Okay, to deal with such notations, we can just say at most countable. If I say at most countable, that means it is either finite or countably infinite. Okay, it's just a notation. I don't think it should be confused. Okay, so I have 2-3 theorems. Okay, they are in the book Eliplantis and Birkinshaw. So number one is actually theorem 2.4. Theorem 2.4 says that every subset of a countable at most countable set is at most countable. Every subset of an at most countable set is at most countable. Okay, that means every subset of a countable set, or I can just say
Either finite or countably infinite.
that's what I'm trying to say. Every subset of a countable set is either finite or else countable. I think I should write large. My handwriting is becoming smaller and smaller. Sorry. Every subset of a countable set is either finite or else countable. Okay? Do you understand what I'm trying to say?
Yes, ma'am.
Yeah, ma'am.
Yes, ma'am.
Okay, so this theorem is actually on page number 10 on the book. So I'll say page number 10. Okay. So in the proof of this theorem particularly, we can use the well ordering principle of mathematical induction. So I can say in the proof, we can use PMI or well ordering principle. Okay, I want you to understand that okay, if you try to think of this statement, that means we have say x1, x2, xn as an enumeration of the set because we have a countable set, right? So any subset of this cannot be larger. Any subset of this cannot be larger. It can be either finite or countable. It can never be uncountable. So a point here I want to make is that suppose I have n. Okay, suppose I have x is equals to n. Now obviously this is countable.
Yes, ma'am.
If I take say y subset of x by y is equals to 2n, such that n in n. Okay, that means 2, 4, 6 dot dot dot. Then again this is countable.
Countable.
Yeah, you know that y is a proper subset of x, but y is actually equivalent to n. This is actually equivalent to x. In this case it is equal to x. Okay, so we have a proper subset of a set. This is a proper subset, but it is actually equivalent to the set itself. Okay.
Yes, ma'am.
Okay. So another theorem says that uh, suppose now it was about subset.
Hello,
When
ma'am.
we have a count, yes.
Ma'am, this theorem we can prove by a one-one mapping.
Exactly.
We define
Yes,
suppose
we can.
a subset and x is set f from a to x, and define identity mapping fx equal to x. Then cardinality of a less or equal to of cardinality of x.
But it's
So first of all, Piyush, we have not defined anything like cardinality now. To say that
Yes.
it is countable, we say this that there is a bijection from n to the set. Okay.
but this is not true for the finite groups.
Cannot
This
be
is only
bijection because
countable
if
in
x
finite.
is finite, subset is finite, then it is not true.
I am saying that it is, oh, I am saying it is either finite or countable. Suppose it is not finite, then it has to be countable. Countable, that means it is numerically equivalent. It is like by as set equivalent to n, which is again equivalent to x. Okay. Any subset can be either finite or countable. So the point I want to mention here is that suppose I have a countable set. Okay, suppose I have a countable set or sets. So I can make different sets from this set. I can take subsets. I can take union of sets if I have many sets. I can take union of sets to make another set. So the question here is that suppose I take union of countable set, then whether it be countable or not, if it is a subset, we know that it is either finite or else countable. So there is again a different way of making sets from another sets. Taking the product. If we have some collection of sets, we can take product of the sets. We see that, right? So in both of these cases, I'm just trying to say that, yeah, in particular situation, that union, in particular situation, the union will be countable, and in particular, or rest all, it will be uncountable. Okay. I'm just trying to make statements here. Statements which you must remember in order to prove further questions. Do you understand? So suppose I want to prove that some set is countable. I can show that it is contained in some bigger set which is countable. Okay. I'm just
Yes,
trying to
ma'am.
give an example. it's just statements. If we have a collection of countable sets, if we have just one countable set, if I take subsets, then they are always either finite or countable. Okay, if I have a collection of now countable sets, and if I take their union, then in which condition the union is countable. So I'm just trying to make a statement. Then union is countable if I take a countable union. Okay, so I'm saying that if we have a countable collection, then it will be countable. That means if I have a countable collection of countable sets, then it is countable. Okay, I'll try to elaborate this. I am saying this is actually theorem 2.6. Okay, if I have a countable collection, that means if we have A1, A2, dot dot dot.
We can index all the sets.
I'm just taking an enumeration. Okay,
Yes,
okay.
ma'am.
I'm just taking an enumeration because we know that if we have countable sets, we can enumerate them. So I'm saying that if we have A1, A2, a countable family such that each AI is countable, then union of I going from 1 to infinite, is a countable sets. Okay, so suppose I have, and it has an equivalent formulation. If that means I can just take they to be at most countable. That means I can take to be either finite or countable. Then also it holds true. So suppose we know that n is countable. So if I take n cross, okay, it's a different thing. I think we will see an example of this in the tute sheet. In the tute sheet, there are examples. Okay. So now the third point which I wanted to make was product of sets. Okay. The product of sets, if I take a finite family of sets, if I take a finite family of countable sets, here we had countable collection of countable sets. In the product, I am saying that the family which you are taking for the product, that family should be finite in order for the product to be countable. So I am saying that if A1, A2 dot 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 AN is a finite family of such that each AI I less than equals to 1 less than equals to n is countable, then A1 cross product with AN is countable. Okay. Here also I can just say that if I take finite set also and I make their Cartesian product, then the Cartesian product will be countable. Does that make sense now? Do you understand what I'm trying to say?
Yes, ma'am.
Yes, ma'am.
Thank you so much. So as an example, I'll give you an exercise. If you take page number If you see page number 13, it has some exercises. Okay, page number 13, problem number 10. And page number 14, problem number 14. No, problem number 11. Okay, they both use these three theorems. Okay, these three theorems are the key. Okay, if you want to prove that some set is countable by explicitly mentioning the bijection, then well and good. But these are like shortcuts. If you know that some set is either a union of some countable sets, then you are good to go. You just state this result and show that by this result and by some equality, the given thing is countable. Okay, this is the key in showing. Do you understand? So I'm just saying
Yes,
that
ma'am.
these are the exercise.
Yes, ma'am.
Okay, one last thing, just 5 minutes, just be there with me. Just 5 minutes. 5 minutes, okay. So 5 minutes, a special case of Cartesian products. Special case of Cartesian product. The special case is that xi, all the sets are the same. If I'm saying I'm taking Cartesian product of xi the family, I'm just saying that my index set is non-empty. I'm saying that the index set I is non-empty, and for each I, some x set is also non-empty, and for each I am choosing xi to be equals to this x. Okay. Okay. So what is product of xi then? Product of xi, we know that function from I to union of xi. But here xi is what? All xi's are x, so the union of xi is also equals to x, right? Such that fi belongs to xi for all I. So if you see this, it just becomes all the function from I to x. So now for the special case, when we have xi, all xi's to be the same, the product is nothing but the collection of all functions. Okay?
Okay.
Very good. So, and see, because in this case, the restriction condition is actually satisfied. It is nothing to be like worried about. Okay? And we have a notation for such a case. See, when we had Rn, we know that Rn was actually Cartesian product of R cross R cross R, right? And it is actually that means product I belongs to the set 1 to n of R. So you see, if I have the product of x, some particular x, I will just say that it is actually, I will denote it by I x to the power I. See here, Rn is actually the product of R, this index set many times. Okay, n is just used to denote the index set 1 to n here. So I am denoting product of x to be x to the power I. That means all the functions from I to x. Okay, in general, if I have for a and b non-empty sets, a to the power b actually then means all the functions from b to a. Okay, it's just a notation. Just try to remember this. It's a notation. Okay, nothing to think about. It's a notation. Apart from this, if we have a if we have a two element set, if a set has two elements, we denote actually we denote its product to be 2 to the power x. Oh, no, 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 no. I'll read. So if I have an set has two elements, say suppose 0, 1, we will denote it by 2. Okay. Okay, it's notation. A set with two
Yes,
elements,
ma'am.
I'm just usually denoting it by 2. So if I have a non-empty collection, a non-empty set X, so if X is non-empty, then 2 to the power X will actually means functions from 0, 1 to X. Okay, and this 2 to the power X is actually equals to, also we denote it by power set of X, and these two are actually the same. These two are actually the same. So therefore we do not have a notational problem. So this thing is actually again the problem number 9 on page
मैम
13. Yeah.
मैम टू द पावर x तो फंक्शन तो x से 0 1 जाएगी ना?
Yes, ma'am. X
No,
to
no,
0.
no. I am saying in the power, whatever is in the power is actually our like first set function from this power set in the power
Yes,
to this
ma'am.
set.
So here
Yes, ma'am.
power is
So
X.
2 to the
So
Function is
F from X to 0, 1.
Yes, ma'am.
ma'am while defining 2
Here
raised to power
power is
x.
X, na? 2 raised to power X.
okay. I think there is some problem. Okay, I'll check the book again. Okay, you all please try to read the notes before the class. Suppose you are not able to read the notes before the class, then after the class, please try to read the notes. Okay, because if you read the notes, whatever problem you suppose still remains in the class, they will be clear. And if after that, if after reading the notes also you are not able to understand something, then you should inform us. Okay, it might happen that there is some problem in my teaching style. So I think the class is over. You can just stop the recording. Okay, I think I can also stop the recording.